Hi everyone, today we're going to be going through the 2017 fall midterm for Organic Chem, and I'll be going through the answers here. Please follow along. Okay, so we're going to start out with question 1, and it says, neratinib is a drug that was approved by the FDA for the treatment of breast cancer in July of 2017. The structure is shown below, and you can see the structure right here. 5 functional groups are circled and labeled A to E. In the spaces provided, write the name of the functional group that corresponds to each letter. So you can see functional group A that is circled right here is a nitrogen with carbons attached to it. That would be called an amine. Not to be confused with an amide. An amide has a nitrogen that is attached to a carbonyl, carbon double bond oxygen, and this one clearly doesn't have that. We have B, you can see circled here, carbon-carbon double bond is an alkene. C, now we have the nitrogen atom connected to a carbon double bond oxygen. This one is the amide. D, you can see right there, carbon triple bond to nitrogen is called a nitrile. And E is circled over here, and it has a carbon bonded to an oxygen bonded to a second carbon, and this is an ether. This is the same molecule again. In this drawing, 5 carbons are indicated by the arrows. For each carbon, write its hybridization, sp, sp2, etc. in the box provided. So carbon A, which is this one here, has a single bond to another carbon, a single bond to a hydrogen that's not drawn in, and a double bond to another carbon. Total of 3 different bonding groups, and that means it's going to be sp2. Carbon B, you can see, is the carbonyl carbon. That's what it's pointing to. It has 2 single bonds and a double. That one's also sp2. Atom C has 2 singles and a double as well, sp2. D has a single and a triple bond. That means it will be sp. And carbon E has 2 single bonds to hydrogen not shown, and a single bond to oxygen and a single bond of carbon that are shown, so 4 single bonds is sp3. Question 2 says, for the following multiple choice questions, write your answer in the box provided. Number 1, for the following set of 5 cycloalkanes, arrange from most to least stable. So just looking at these, the one that would jump out at me as probably being least stable would be D, because it has a 3 carbon ring, a cyclopropane ring, which has very severe angle strain. In terms of angle strain, the lowest would be E. D is the worst. B and C would be pretty bad as well. And then A would be not so bad. E is actually going to be the best of all of these for a number of reasons. First, it has no van der Waals strain because it has no substituents off the ring. It has no angle strain because all the bond angles are 109.5, assuming it's in the chair conformation. And it has no torsional strain because all the CH2s around this ring are staggered. Or it's got minimal torsional strain is what I should say. So the correct answer, so the most stable is, so it wants from most stable to least stable. So the most stable is going to be E. It's going to be more stable than the next ones. So the second one in terms of stability is going to be A, because it has a 5 carbon ring. Angle strain is minimal in a 5 carbon ring. Torsional strain is worse definitely than cyclohexane. Then we're going to compare B, C, and D. The worst we said was going to be D, which we can put over here. But we have 2 more spots, B and C. So we have to decide which of these, B or C, is going to be more stable. In B, we have the 2 substituents, which are 2 methyl groups, quite close to each other, and they're cis. So they're both pointing in the same direction. That's going to maximize van der Waals strain for those 2 CH3 groups because you're bringing them very close to each other in space, whereas in C, those 2 methyl groups are spaced very far apart. So I would guess that B is going to be more stable than C, and that gives us E, A, B, C, D, which is E, is our correct answer. Number 2, out of the 5 following alkanes, which will have the highest boiling point? So I think these are all isomers of each other. They're all, this one's C8, H18, 1, 2, 3, 4, 5, 6, 7, 8, C8, H18, C8, H18, and so on. So these are all isomers of each other. So what we notice is that if you increase branching among isomers, boiling point goes down. And that's because surface area goes down as you increase branching. So the highest boiling point is going to be the one with the least branching, which is B. Which of the following molecules is not an isomer of the other 4? So what we would want to do is look at the molecular formula for each of these. You may be able to tell right away that D and E definitely are not going to be isomers of each other because one has a double bond. They're similar in structure, except one has a double bond and one doesn't. So that's going to create a difference of 2 hydrogens. But what you can do for each of these is just count all the atoms up and come up with the molecular formula. The one that has a different molecular formula from the others is going to be the one that's not an isomer. So for E, if you want to start on the right side, you can count up the carbons, and there's 6 carbons. In terms of hydrogens, we have 3, 2, 2, 2, 1. So it's 3, 4, 5, 6, 7, 8, 9, 10 with an oxygen. This second one here, again, has C6. If you count up hydrogens, you have 3, 1, 2, 2, 2, 1, 1. And that equals 12 if you add all those up. So right away, D and E are not going to be isomers of each other because, as I said before, they differ by 2 hydrogens. Let's see what all the other ones have. If you look at C, it has, again, 6 carbons, 3, 1, 2, 2, 2, 1, 1, 12 hydrogens, and 1 oxygen. So C and D are isomers. E is the odd one out so far. And we can go down the list and find that both A and B is doing the same thing, also are C6H12O. So the odd one out is going to be E. Number 4, what's the geometry of the nitrogen atom in methamphetamine? Well, first of all, we have to know what electron groups are on there. Because this is a bond line structure, there can be lone pairs that aren't shown. So this nitrogen actually has a lone pair on there that we don't show in a bond line structure. We know it's there because it has to have a full octet with 3 bonds in order to have a neutral charge. So that is what the nitrogen looks like. It has 3 bonds and 1 lone pair, 4 electron groups. So the geometry of the electron groups is going to be tetrahedral. The actual geometry of the atom, the shape of the atom, because when we look at the shape, we don't count lone pairs, will be trigonal pyramidal, which is C. Not trigonal planar. I think trigonal planar would be the one, if you forgot about the lone pair and just looked at the bonds, you might be tempted to go with trigonal planar, but don't forget about the lone pairs that are there as well. Number 5 says, which of the following alcohols will have the highest pKa? Highest pKa means weakest acid. Stronger acids have lower pKa's. So in terms of acidity, these are all OH acids. And so you can't rank them based on the atom the hydrogen is attached to, because it's always oxygen. And none of these have resonance structures, so the difference between these is going to be the presence of nearby electronegative atoms. All of them have fluorines attached. We're going to be looking at the number of fluorines and the proximity of the fluorines to the OH group. The closer the fluorines are to the OH, the bigger the impact they will have on the pKa. Fluorines, because they're electronegative, will lower the pKa, make these things more acidic. So E has 2 fluorines very close to the OH. That will be the strongest acid out of all of these because highest number of fluorines, and those fluorines are closest to the OH group. So that's not what we want. We want the highest pKa, which is the weakest. So the weakest here is going to be A, because it only has 1 fluorine, and that fluorine is as far away from the OH as possible. And I guess to rank them, the weakest would be A, followed by B, followed by C, followed by D, followed by E. These are sort of written left to right in order of increasing acidity. Question 3, for the following multiple choice questions, write your answer in the box provided. Below is the structure of morphine. Which of the following functional groups is not present? A, aromatic ring, we have an aromatic ring right there, so that's not it. Amine, we have an amine right here. Amide, I don't see, so I think amide is going to be our answer. Ether, we have an ether group right there, and an alcohol, we have an alcohol down here. That's technically not an alcohol. If you saw my Instagram post about this, that's an OH on an aromatic ring, has a different name, it's called a phenol, which according to IUPAC rules does not count as an alcohol. Question 2, which of the following molecules gives rise to the IR spectrum below? So the way I'd handle IR spectroscopy questions is the first thing that I would do is draw a vertical line at 3000 and a vertical line at 1600. So if we go over to 3000 here, you can draw a vertical line that goes up like this. And if you start at 1600 and go up like that, you can see I've got now two straight lines. Everything to the right of 1600 is the fingerprint region, which we generally largely ignore. There's two stretches in there that we sometimes look for ethers and for esters. But what else we see here, one thing that jumps out at me for sure is this right here, which is a triple bond. If that was a carbon-carbon triple bond that was part of a terminal alkyne, like B, then what you'd also expect to see is out around 3300, a very strong, sharp peak around the same place you find an OH, but not broad like an OH. We don't see that here, so we know this can't be a terminal alkyne, so we know B is kind of off the table here. We can also get rid of E because it's also a terminal alkyne. We know it can't be a terminal alkyne. And we can get rid of C because C doesn't have the triple bond stretch. So we're down looking between A and D. D we can kind of rule out though, because D has a feature, or should have a feature, that we don't see in our spectrum. This has a carbonyl group which gives around 1700, 1720, a very strong band, and you see this is 1700 right, no, that's 18. This is 17. And you can see up here there's no carbonyl double bond. If it was there, it would be obvious, it would be strong, and it would be down at like, you know, it'd be down here, it'd be down at like 0% transmittance. But we don't see that, so we can rule out D as well, which gives us A. So that's a nitrile, that triple bond that we're seeing, that C triple bond N. The other thing that we can see here is a pretty weak peak around 1600 reciprocal centimeters. That's where you find CC double bonds, which we have in this molecule. Also, if you look out at 3000, we see stuff to the right of 3000, which is sp3ch stretch. And there's stuff to the left of 3000, which is sp2ch stretch. And this molecule has sp2 carbons with hydrogens on them, and it's got a bunch of sp3 ones as well. So everything in this spectrum matches A. So I'm going to put A in our box here. Next question says, the sigma bond in propyne indicated by the arrow below results from overlap of an blank orbital on carbon 2 and n blank. So I guess it's an sp2 or an sp3 or an sp. So what we would do is we would look at the carbon atoms 2 and 3, identify their hybridization. Carbon 2 is sp hybridized, carbon 3 is sp3. Whenever you have a carbon-carbon bond, it will be the result of overlap of hybridized orbitals. So it'll be an sp overlapping with an sp3, which is option E. Question 4 is looking at Newman projections. Which of the following Newman projections represents the most stable conformation of 1-chloropentane? So we can probably get rid of D and E right away because those are eclipsed conformations, and eclipsed conformations will not be the most stable conformation. The most stable conformation will be a staggered one. If you look at A and we start counting carbons, that dot in the center is carbon 1, and then the big circle behind it is carbon 2, 3, 4, 5, 6. So this chain has 6 carbons in it, so that's going to be a hexane, not a pentane. So it can't be A. B, if you count, we have 1 for the little dot in the center, 2 for the big circle, 3, 4, 5. So that's pentane. Okay. C, 1, 2, 3, 4, 5. So B and C are possible candidates. They at least have a pentane chain, and both of these have, well, not both of these. If you, I guess the way I numbered this chain isn't quite right. So if we start at this end, 1, 2, 3, no, 4, 5. This does have the chlorine on one end of the chain, which we would call carbon 1. It has the rest of the chain, anti. If you look at the geometry between the chlorine and the rest of the chain, they're anti, which is more stable than the arrangement we have in B, which is gauche. So C is our preferred answer for this one. For the following molecule, how many sp3 hybridized carbons are there? So this one is sp3. This is sp2, 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 2, 2, 2, 2, 2. That one is sp3. And these two are both sp3. So that gives us a total of 4, which is D. Number 4, draw examples for each of the following provided. Tertiary alcohol. So it's carbon with an OH, right? It's got an OH. But the carbon that has the oxygen must be bonded to 3 other carbons. This is just one example. This is maybe the simplest example, tertiary butanol. Aromatic hydrocarbon, benzene, simplest example. Secondary carbocation, so that's a carbon that has a positive charge, and that carbon is bonded to 2 other carbons. So you can see 1 and 2. A molecule with high angle strain, so something like cyclopropane would be way up there. Cyclobutane is pretty high as well. A molecule that has a larger ring I probably wouldn't necessarily include here. Cyclohexane has the best for having almost no angle strain, but those two have pretty high. This one says 1,2-cis-dichlorocyclohexane. I guess there's 2 ways you could draw this. One is you could draw it like Cl, Cl. So those are cis, or you could draw it like a chair. Something like that. I mean, there's lots of different ways you could draw that correctly as a chair. This is just one possible way of drawing that conformation. Number 2, draw complete Lewis structures, show lone pairs, formal charges. Let's do this. We got oxygen, sulfur, oxygen. Adding up lone pairs, we have 2 times 6 for the oxygens. Sulfur is 6 is 18, minus 4 for the 2 single bonds is 14. 2, 4, 6, 8, 10, 12. And extra atoms go in the central atom. That gives us 14. We now need to make a multiple bond to the sulfur to give it a full octet. So now we have only 2 lone pairs on that oxygen. Sulfur, oxygen. And if you calculate formal charges for this, the oxygen gets -1 and the sulfur gets +1. What we can do is actually get rid of those formal charges if we make a second multiple bond, and we have sulfur, lone pair, oxygen, oxygen. Now we can only make that second multiple bond because sulfur is in the third row or below, that exceeds the octet on sulfur, but you can exceed the octet on elements that are not in the second row. So if they're in third row or lower, which sulfur is in the third row. Next one, we have a carbon, hydrogen, hydrogen, oxygen. So this one, if you add up the electrons, carbon has 4, 2 hydrogens has 1 times 2, the oxygen has 6, which gives you 12, minus 6 for the single bonds, leaves you with 6. Fill up outer octets, 2, 4, 6 is 0. The carbon doesn't have a full octet, so we need to bring 1 electron pair down. When we do that, we end up with a multiple bond between the carbon and the oxygen, and now everything has a full octet, everything has 0 formal charges, and we're done. B, draw the Lewis structure for the sulfate ion SO4 2- and 2 resonance structures for a total of 3. Show all electrons and formal charges, blah, blah, blah. Sulfur, oxygen, 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 oxygen. It's going to be our first sulfate. If you follow the regular rules, we're going to say we have 4 times 6 electrons for the oxygens. Sulfur is going to add another 6, and the -2 charge is going to add 2 electrons. So that's 24, 32. Minus 8 electrons for the 4 single bonds we already made. Gives us 24. And now we fill up the outer octets. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We used all of them and just filled the octets of all of the outer atoms. Now if you look at formal charges, the sulfur will get a +2 and all the oxygens will get -1. And so this is clearly not going to be the best structure because the sulfur, we almost never have a good Lewis structure where any atom has a +2 or a -2 charge. So what we can do is bring an electron pair down actually on 2 different oxygens. And what that will do, I'm going to just erase this stuff, the numbers. That will convert it to sulfur, oxygen, oxygen, O minus, O minus. So this structure is better. We again exceeded the octet on sulfur, which is doable because it's in row 3. And we have 2 oxygens with negative formal charges, which is okay because this is a charged structure, as you can see from the question. So you can't get away from having formal charges somewhere in this molecule. Now we're being asked to draw 2 more resonance structures for this, and we can do that. When we made those multiple bonds, we could have opted to put those multiple bonds anywhere. So what we could have done was push electrons from, say, the right-hand oxygen up to the top oxygen. And what that would have done is make a molecule that looks like this. These oxygens were left untouched. Now we have a multiple bond to the right oxygen, and the top oxygen has 3 lone pairs and a negative charge. We can do that again. We can, I don't know, let's put there. Now you get sulfur, single bond oxygen, double bond oxygen down here, double bond oxygen over on the right, single bond up here. Good. 6, draw both chair conformations, and here the chair is sort of drawn already out for you, of trans 1,3-dibromocyclohexane using the template provided. Carbon 1 and carbon 3 are already drawn. Indicate which is more stable. So in our structure, that's 1, 2, 3. The way I'd look at this is say there's a hydrogen on carbons 1 and 3 each that are going back. So I would say the 2 bromines are up and the 2 hydrogens are down. So if you look on carbon 1 on our template here, is going to have bonds in this direction. Carbon 3 has bonds in that direction. If you look at the direction, you should have bonds that are either straight up or straight down, which are the axial ones, and the equatorial bonds should be parallel to a bond that's 2 bonds away. So this is parallel to this. This is parallel to this. All right. So in these positions, I would say that the one that's going up is up, and this one is down. This one is up, and this one is down. Up and down are relative terms here. It doesn't mean, up doesn't always mean axial. Up can be equatorial if it was on a different carbon. But anyway, we have the up position is Br, and the down position is hydrogen. Up position is Br, down position is hydrogen. Then we have on the ring flipped structure, carbons 1 and 3, where 3 is down, 1 is down, will be axial. And you can kind of tell, if you look at the 2 bonds coming towards carbon 1 down here, it's almost like they form an arrow, you know? It's kind of caving down, so it means the axial there is going to be down as well. They both have an equatorial as well. Again, equatorial bonds should be parallel to something 2 bonds away, like that one. And it's going to have an equatorial, it's kind of coming at that angle, which should be parallel to that bond right there. Now, again, the BRs are in the up position, and the hydrogens are in the down position. You see in this structure, up doesn't mean axial, up means equatorial. Up relative to the other group that's on the same carbon. All right, we're done. It's asking which is more stable, or if they're equivalent. This one is going to be more stable because it has both groups in equatorial positions. B, draw the most and least stable Newman projections for 1 butanol. So I'd start out by drawing 1 butanol somewhere. If you get that part wrong, it's going to be tough, tough climb ahead. And you're looking down the C1, C2 bond. Okay, this is C1, this is C2. Our I is here, our pink eye. We weren't being very hygienic, we got pink eye. All right, that's it. So what else does this have? This also has 2 hydrogens. And carbon 2 also has 2 hydrogens. So what we're going to be looking at then is, in the most stable, we're going to have carbon 1, and then a big circle for carbon 2. Carbon 1 will have an OH. Looking from that angle, you know, carbon 1 is going to have an OH that's down. It's going to have a hydrogen off to one side and a hydrogen off to the other side. Carbon 2, which is behind it, has 2 hydrogens and an ethyl. So the most stable conformation is going to have the ethyl group anti to the OH. That means it's going to be up here. That means there's also a hydrogen here and a hydrogen here on the back carbon, carbon 2. All right. Least stable, basically what we're going to be doing is rotating around that carbon 1, carbon 2 bond to, it's going to be an eclipsed conformation, and the worst is when the 2 groups are close, very close to each other. So that's going to look again like this, and if you have the OH up here and the ethyl group pointing in the same direction, this is going to be the worst, the least stable conformation. Question 7 says, for the following multiple choice questions, write your answer in the box provided. Which of the following molecules has an oxygen with a formal charge of +1? So you can go through each one of them and calculate formal charge. This one has a -1. This one has a 0. This one has a 0 and a -1. This has a 0. And this has a +1. So the answer is E. To calculate those, formal charge is just taking the number of valence electrons for oxygen, which is 6, subtracting the number of bonds it's making 3 bonds, and subtracting the number of electrons that are found in unshared pairs. which in this case is 2, leaves you with +1. Which is the correct ordering of acid strength for the following compounds from weakest to strongest? Okay, all of these are OH acids. All of these, when they lose H+, will make an anion that's resonance stabilized, although 3 is going to be the worst of them because the resonance form for 3 is going to have this in resonance with C, H2, negative O. You can see that half clearly here. That's not as good as having a resonance form where both forms have the oxygen with a negative charge, because carbon is not very electronegative. It's not as helpful at stabilizing that negative charge as an oxygen would be. So the weakest here is number 3. We want weakest to strongest, so already we're kind of torn between B and D, because A, C, and E has chosen something else as the weakest. The strongest is going to be, because 1, 2, and 4 are all very similar in structure, except they have different numbers of electronegative atoms. Well, different numbers or different types. 1 doesn't have any, 2 has a chlorine, and 4 has a fluorine. 4 is going to be the strongest of this trio because fluorine is best at stabilizing the conjugate base, which makes this acid a stronger acid, because fluorine is the most electronegative compared to chlorine, or in the case of 1, hydrogen. So we can cross B off because B doesn't have 4 as the strongest acid, so D is going to be the correct answer. We've identified the strongest, we've identified the weakest, and then the other two will be the second strongest and 1 will be the third strongest. Question 3, which of the following molecules matches the IR spectrum shown? Just looking at this, first thing we're going to start at 3000, and we're going to make a vertical line there. We're going to do the same thing at 16, right there. And we see a couple of things. Remember, this is fingerprint. What I can see here is what looks like a carbon double bond oxygen and a carbon double bond carbon. Over at 3000, you can see there are CH stretches. It is not super clear to me if there's both sp3 and sp2 CH stretching there. You can see there's a little bit of something just to the left of 3000, but I'm going to reserve judgment there until I look at the possible structures that we have. One thing we can do right away is rule out B and rule out C, because those are carboxylic acids. Those give you a very strong band that ranges from about 3500 down to like 2500. It covers like that whole left part of the spectrum, which we don't see, so I don't think those are there. Next, E has an OH. OH has a big band out at 3500 or 3400. It's not there either, so we can cross that out. And we're down to between A and D. Both of them have this carbon-oxygen double bond. But the main difference between A and D is A has a carbon-carbon double bond and D does not. Now we see this carbon-carbon double bond in the IR spectrum. So we're pretty sure it's A. A does have a single sp2 CH stretch. So maybe that's what's giving rise to this little thing just to the left of 3000. Which of the following cations is most stable? This is a secondary carbocation. Secondary carbocation. You can tell it's secondary because the carbon with the positive charge is bonded to 2 other carbons. This is secondary. This is tertiary because the carbon with the positive charge is bonded to 3 other carbons. And this one is primary. The best one is going to be tertiary, which is D. Number 4, which of the following cation isomers receives the greatest amount of resonance stabilization? Which is most stable? So this is a tough question for a lot of people. I remember when we gave this midterm a while back. What you basically do is you make resonance structures, and whichever one can make the greatest number of resonance structures is going to be the one that's most stable. So if you look at A, what you can do with A is you can move a pair of electrons over and make a resonance form that looks like this. Positive charge there. You can also push it back and move that pair over, which gives you a resonance form which looks like that. And there's another one yet we can do, which looks like that. So this has a total of 4 possible resonance structures, the 3 we drew and the original structure itself. Get rid of all that. If you look at B, B you can't do any resonance structures for, because B has hydrogen, hydrogen, hydrogen. The adjacent atoms don't have any lone pairs or double bonds to make resonance structures with. So this only has one structure, which is the one drawn. C, you can actually make a total of 3 structures for. You can move one lone pair, which pushes the charge here, or you can move both lone pairs, which pushes the charge here. This one is isolated from the rest of the double bonds, so you can't make any resonance forms, including that double bond. This one has 2. You can put the charge over here, and that's it. These 2 electron pairs are also isolated. And E, you can put the charge here. That also has 2. These double bonds are also isolated. So the winner is 4, is A, because it has 4 possible resonance structures you can draw. That means that charge gets spread out over 4 atoms, and that greatly stabilizes the structure. We don't like buildup of charge. Draw 4 constitutional isomers C4H8O2 in which one isomer has an alcohol functional group. One has a ketone, one has an ester, and one has a carboxylic acid. So C4, 1, 2, 3, 4, if you made a molecule like this, I guess we need another oxygen somewhere. Let's put one over here. Let's count up our molecular formula for this compound. We have 1, 2, 3, 4, so that's C4. H, there's 2, 2, 2, and 2, and then 2 on the 2 oxygens makes 10 O2. So we have 2 hydrogens too many in this particular structure. So what we can do to get rid of 2 hydrogens is one of 2 things. We can make a ring, or we can make a multiple bond. Let's make a ring. Why don't we instead make a ring with 4 carbons, OH, OH, like that. That's an alcohol. With 2 OHs, we call them diols. It's obviously not the only possible structure. There's dozens of other structures. You could have had one like the thing we first drew with a double bond in it somewhere. A ketone will have 4. That'd be a ketone right there. This is C4, H, 1, 2, 3, 4, 5, 6, 7, 8, O. So we need another oxygen somewhere. And we can't put that oxygen near the carbonyl group, or we'll turn it into an ester. So what we're going to do instead maybe is make this an OH. And that makes it O2. So that's got a ketone and an alcohol. In fact, if you wanted, you could have made that structure and used it for your answer for both of the first 2. An ester, not so quick. Ester is going to have this group. So this one is C4H, there's 3, 2, 3 is 8, O2. And a carboxylic acid, I mean, you can kind of like lop off the ethyl group here and put it on the other end of the chain. There's the ethyl, there's the carbon, there's this, and we have an OH. That is going to be C4H8O2. Number 5, complete the structures on the right so that they are the ring-flipped forms of the molecules on the left. Spent a lot of time in Unit 4 doing this. So carbon 4, you can see, has a hydrogen not drawn and a methyl. This is in the up, this is in the down. So in 4, we need positions here and here. For the up one is going to be the methyl, and the down one is still a hydrogen. We leave them in either the up or down form, depending on where they were in the starting compound. On carbon 1, we have an OH that's down and a hydrogen that's up. Carbon 1 looks like this. Hydrogen is down, OH. OH is down, hydrogen is up. OH is axial, hydrogen is equatorial. Now, one thing to remember, if you've done this correctly, in a ring flip, any group will swap from axial to equatorial or vice versa. And that's what we see. On the left, the methyl is equatorial and the OH is equatorial. In the flip form, both of these are axial. Question 2, on carbon 5, you can see carbon 5. I always find it helpful to draw in the hydrogens. Carbon 5 is going to have 2 groups, and carbon 2 has 2 groups here and here. Carbon 5, the up group is hydrogen and the down group is methyl. Carbon 2, the up group is hydrogen, the down group is isopropyl. By up and down, by the way, I just mean like which one is closer to the top of the molecule, up and down. It's relative between these 2 groups. Next one, C, has a couple of atoms going on here. We have atom 5 with a hydrogen, atom 4 with a hydrogen, atom 2. All the hydrogens here are axial. Next, carbon 5 is going to have 2 groups, carbon 4 and carbon 2. So if it's just CH2, don't bother drawing them in. It just makes the structure messier. So looking at the left-hand structure, I'm going to say that the hydrogen is up and the chlorine is down. Relative position of those 2 groups. This one is up, this one is down, and this one is up and this one is down. So let's go back to our structure on the right. On carbon 4, that's where we have the chlorine. The chlorine is up, the hydrogen is down. On carbon 5, the hydrogen is up and the chlorine is down. On carbon 2, the hydrogen is down and the T-butyl group is up. Notice all the equatorial substituents on the left got swapped to axial positions on the right. Question 9, add curly arrows to show the movement of electrons leading to the breaking and formation of bonds. And so what you can see in the first example, it's trimethylamine reacting with HCl. What we notice is the nitrogen goes from 3 bonds to 4 bonds. It's picked up a hydrogen, it's made an additional bond, and it's lost a lone pair. So the way we draw this is we have an arrow that starts at the lone pair of nitrogen and goes to the hydrogen that it's forming a new bond with. So that means that that lone pair on the nitrogen is being converted into an NH single bond. At the same time, the HCl bond breaks, and the pair of electrons in that bond moves on to the chlorine, so it goes from 3 lone pairs to 4 lone pairs and a negative charge. Next one, a lot's going on in this one. You're going from 2 molecules to 3. What's happening is you have a hydrogen that's being removed by the base, by OH minus. At the same time, the carbon-chlorine bond is breaking. So one thing we can draw maybe right away is that carbon-chlorine bond breaking. That shows the pair of electrons in that bond migrate over to the chlorine to make another lone pair, which gives it 4 lone pairs and a negative charge. We know the OH is forming a new bond, so we can draw a curly arrow starting at the oxygen going to the hydrogen. And the last thing that happens is the CH bond breaks, and where do those electrons go? Well, we see that there's a new bond in the product. There's a carbon-carbon double bond, so we can push those there and make that. Next, 9. The following molecules are drawn with all lone pairs and hydrogens shown. The only thing missing is formal charges. Add the formal charges, if any. So the first one has a nitrogen, which has a positive formal charge because nitrogen has 5 valence electrons, it's making 4 bonds, and it has 0 unshared electrons, which is +1. In this example, that oxygen, this is ozone, has 6 valence electrons to start out with, minus 3 bonds it's making, minus 2 electrons that are not shared is +1. This oxygen is 6 minus 2 bonds, minus 4 electrons is 0. So we don't put anything if there's 0. This one is 6 minus 1 bond, minus 6 electrons is -1. So we put a -1 on that oxygen. Over on the right, you've got to be very careful with this one. We have to look at every single atom. And if you look at the previous examples, the ones that we focused on were the heteroatoms, the non-carbon hydrogen atoms. So if we look at that heteroatom, nitrogen, it has 5 valence electrons, minus 3 bonds, minus 2 is 0. It doesn't have a formal charge. In fact, only one atom here does. And it may be hard to spot at first, but it's right in there. That's a carbon, which has 4 valence electrons, minus 3 bonds, minus 0 unshared electrons is +1. So this is a carbocation. It's a positive charge on that one right there. Number 10, each of the following IR spectra has one of the compounds A to F. So this is IR spectroscopy, but a whole bunch of examples all at once. So what I like to do in a question like this is, first of all, look at each of the spectra and see what features should be maybe a little obvious to us here. Let's go 3000 and make our vertical line. Let's do the same thing at 1600. Didn't work for me. There we go. Vertical line there. This is fingerprint region. This looks like a C double bond O. This is 1700. So it's between 1700 and 1800. It's very strong, goes right to the bottom of the page. So I'm pretty confident that's what that is. If you look at the numbers here, that's 29, 28, 27. 27 and 28, there looks to be a pair of peaks here. That to me looks like a Fermi doublet, which is indicative of aldehyde CH. We do have an aldehyde somewhere here, F. So I'm leaning towards F for this first one because it's got the carbonyl group and the Fermi doublet. The rest of this stuff in here is all sp3 CH stretch. So I'm going to tentatively put F here, realizing maybe we'll revise if we see something else in the other spectra. This one, we do the same thing as before. And 1600. Come on now. So what we see again, it looks like another carbonyl group. This is fingerprint region. That looks like sp3 CH stretch. There doesn't appear to be any carbon-carbon double bonds. There doesn't appear to be any sp2. There's no alcohol. There's no acid. There's no triple bonds. This looks like maybe a straightforward ketone, possibly an ester. Maybe that's some ester stretching in there. If I was to look at the candidates here, it's definitely not D, definitely not E, definitely not C. It could be B. I think B is the only reasonable option here. And we know it's not F because there's no Fermi doublet, which you'd find out here. Okay, so far so good. Here, this looks like an OH, an alcohol, ROH stretch. 3000 and 1600. This is fingerprint. A lot going on here. Not a lot going on in the double bond region. Not a lot going on in the triple bond region. No carbonyl, no carbon-carbon double bond, no Fermi doublet. Bunch of sp3 CH stretches. And an alcohol. This looks like a simple aliphatic alcohol. A simple alcohol with all single bonds. Which, if I was to pick, would probably go with A, because the only other alcohol is E, which has a carbon-carbon double bond, and we don't see any sign of that double bond. So let's call this one A. This next one does have another OH stretch. It does have what appears to be, I'm going to get there in a second. CC double bond. That's what that looks like right here. CC stretch. We see again sp3CH stretch. But look at this peak in there. Right? That one could be an sp2CH stretch. So this looks more like an alcohol where there's also a carbon-carbon double bond. So an alkenol, which if you look back at our list of options, does match with up with E. We've already used these ones. So let's call that one E. Next one, let's do the same thing as before. And you get something like this. This is the last one, right? So we're down to two options. We're down to D and C. So D and C should be pretty easy to tell apart. One's got a double bond and sp2, the other one does not. So right away, looking at this last one, if you look out here, you can see there's sp3 CH stretches. And looking there, you can see sp2 CH stretch. So yeah, this has evidence of single bonds and double bonds with hydrogens on them, which to me would kind of seem to rule out C, making D kind of maybe our more obvious choice. Let's see what else we have here. We have this, which is between 16 and 17, which is where you find carbon-carbon double bonds, which matches the structure. Also, you see out here a pretty strong peak around 1200, which is, and I know this is fingerprint, but ethers, which is what we have here, do give strong peaks out there as well, which gives us compound D is our most likely. Now, notice that this peak here is a little weird looking. It's kind of stronger than you'd normally expect to see for a carbon-carbon double bond. It looks more like a carbonyl, except it's in the wrong place. The other thing is it kind of looks like there's like a double peak, like there's two little mini peaks on the end there. That's due to a peculiarity of this particular molecule, where that has lone pairs. This has a resonance structure, which looks like this. Now, this second form is nowhere near the favored form. This one is definitely better because nothing has formal charges, where that same can't be said for the second structure. But what it does show, at least, is that there is communication, I guess is the word we'll say. We'll get much more into detail about this sort of interaction in Organic 2 and future chemistry courses. But when you have an atom with lone pairs immediately attached to a carbon-carbon double bond or an aromatic ring, there is what we call communication between those two groups, and the alkene no longer behaves like a standalone carbon-carbon double bond. It's more like a three-atom system, and that can give you two different stretches. One's called a symmetric, one's called an asymmetric stretch. We're not going to get into those sorts of details, but some bonus learning for you if you're looking for it. I think that's it. That's it for our exam. We can go right back to the first page and we can give ourselves a grade. There, let's go with 100%. Great. Have a great day.